Now we are going to see two-dimensional heat equation. Sometimes it is called Laplace equation, right? So now we are going to derive two-dimensional heat equation. Previously we saw one-dimensional heat equation and derivation and related problems, right? So we'll see the derivation of two-dimensional heat equation. Consider the heat flow in a metal plate x over y. If the temperature depends only on xy coordinate and the time t and does not depends on z coordinate, there is no z coordinate, that means only x and y coordinates, this is two-dimensional heat flow, right, of the plate x over y, right? So z axis is 0. Now consider the rectangular plate ABCD with uniform thickness h. So thickness of the plate h, density of the plate rho, and thermal conductivity of the particular material, right, of the plate, thermal conductivity K, specific heat capacity is small s, with side length we are taking small, very small length, del x del y respectively along x and y axis. So x axis, y axis, 0 0 comma 0. So this is the plate ABCD. So we are taking a x comma y coordinate and given AB which is equal to del x, because side length, right, along x axis AB del x length and BC along y axis, that is del y, right? Now B coordinate, so x plus delta x, y coordinate is same, right? And C coordinate x plus delta x, then y coordinate y plus delta y, so the length delta y. Then D is x comma y plus delta y, right? We know that the quantity of heat inflow or outflow any side of the plate is proportional to the thickness, that is thickness, side length, and the temperature gradient normal to the side. The quantity of heat entering in the plate ABCD per second through the surface AB, so it is going inside from the surface, so minus K H del x dou u by dou y right? The quantity of heat entering the plate ABCD per second through the surface AD is minus K H del y dou u by dou x, right? So the quantity of the heat flow out of the plate ABCD as per per second through the surface CD is minus kh del x dou u by dou y, y plus del y, right? So based on that coordinate, right? And the quantity of heat flow out the plate ABCD per second through the surface BC, right? So BC is minus kh del y dou u by dou x, x plus del x. Hence the heat gain by the rectangular plate ABCD is the heat entering into the plate minus the heat out of the plate, right? So difference between entering and out of the heat flow, right? So minus kh del x dou u by dou y, y minus kh del y dou u by dou x, x minus kh del x dou u by dou y, so inflow minus outflow, right? Minus kh del y dou u by dou x, x plus delta x. So minus kh del x dou u by dou y at y minus kh del y dou u by dou x at x, so minus into minus plus kh del x dou u by dou y, y plus del y. Similarly plus kh del y dou u by dou x at x plus delta x. So kh is common, take it outside. So writing the plus term first, dou x del x dou u by dou y, y plus del y minus del x, we are grouping del x del y term, right? Minus del x dou u by dou y, y plus del y dou u by dou x, x plus delta x minus del y dou u by dou y, dou x at x. Now k h del x del y, we are taking del x del y outside, so we will get first term dou u by dou x, already del x is there, so del y is not there. First two terms del x is there, del y is not there, so divided by del y, so dou u by dou y, y plus del y minus dou u by dou y at y whole divided by del y. Similarly, in the second two terms, del y is there, del x is not there. So we are going to divide the whole term by del x, right? Dou u by dou x, x plus del x minus dou u by dou y at x by del x, right? That is equation number 1. The rate gain of heat by the area ABCD is given by rho del x del y h s dou u by dou t, right? So that is equation number 2. So from 1 and 2, so rho del x del y h x s dou u by dou t is equal to kh del x del y dou u by dou y at y plus del y minus dou u by dou y at y divided by del y plus dou u by dou x at x plus del x minus dou u by dou x at x all divided by del x. So dou u by dou t, which is equal to, we are cancelling h del x del y, right? So remaining on the right hand side, you are having rho and s. So we are bringing that to right side, so it will go to the denominator. But in the left hand right hand side numerator, you are having k. So k by rho s into dou u by dou y at y plus del y minus dou u by dou y at y whole divided by del y plus dou u by dou x x plus del x minus dou u by dou y at x whole divided by del x. Taking limit and del x tends to 0 and del y tends to 0, we have dou u by dou t, which is equal to k by rho s. We are taking the limit on the above term, right? So dou u by dou t is equal to k by rho s. So this is normally, we know differentiation f y plus del y minus f of y by del y, as limit delta y tends to 0, that is f dash, differentiation definition. But instead of f, you are having dou u by dou y. So differentiation of dou u by dou y. So what is that? Dou square u by dou y square for the first term. Similarly, for the second term, dou u by dou x differentiation, dou square u by dou x square. Let k by rho s is equal to alpha square, dou u by dou t is equal to alpha square into dou square u by dou y square plus dou square u by dou x square, which is the two-dimensional heat equation, right? That is equation number 3. Suppose if you are considering steady state, right, of the heat u, which is the independent of time t, right? So dou u by dou t equal to 0, right? Because steady state, there will be no time, right? So we are not considering time on that, right? So if you are considering time, then that is transient state, right? So dou u by dou t equal to 0. So 3 implies dou square u by dou y square plus dou square u by dou y square x square equal to 0, which is the two-dimensional heat flow equation in steady state. This is called two-dimensional Laplace equation. Thanks.